In this lecture, you'll get to know yet another component, the diode. We'll kick things off by exploring the concept of covalent bonding, setting the stage for our understanding of semiconductor materials. From there, we'll learn about semiconductors and the concept of doping. We'll then dissect the p-n junction for you to understand the workings of a diode. Diodes are indispensable in flight computer design, serving various critical functions such as reverse current protection, voltage limitation, and indicating use of flight states. This video is brought to you for free thanks to JLC PCB, the go-to platform for PCB prototyping and manufacturing. I've been using JLC PCB ever since I started designing PCBs, and it's been an incredibly seamless experience. What keeps me coming back is the convenience. They make it simple to upload your designs, choose your specifications, and get professional quality PCBs delivered. Whether you're creating your first PCB or pushing the boundaries of an advanced design, JLC PCB is a trusted partner you need. Check them out at jlcpcb.com and see why so many makers, including myself, rely on them. At the very beginning, we explained that atoms bond with each other to form a different structure. We also said that we can separate the elements in the periodic table into metals and non-metals. Further, we mentioned that metals bond with metals through metallic bonding, while non-metals bond with non-metals through covalent bonding. To describe semiconductor, we have to be aware of the concept of covalent bonding. Remember, every atom wants to have a full outer layer of electrons. The outer layer of non-metals is almost complete, so they might only lack 1 or 3 electrons. For them, it is easier to acquire the additional electrons than to give up all their electrons they already have. In covalent bonding, two elements that lack electrons unite and share 1 to 3 electrons with each other. Through that, both elements reach the desired state and have an equivalent of a full valence layer. The electron of the first element is then also attracted to the nucleus of the second element, and the electron of the second element is also attracted to the nucleus of the first element. A conductor is a material that allows charged matter to move freely. An isolator, on the other hand, is a material that has no freely moving electrons, making current impossible to occur. Then there are semiconductors. These have a full outer layer and also no freely moving electrons. However, if a large enough potential is applied, the electrons can move and the material becomes conductive. The most used semiconductor material is silicon. Pure silicon is a structure that consists of many silicon atoms, each bonding with 4 other silicon atoms covalently. Most electrons are bonded in this structure. However, there are few electrons that can escape their bonds by getting enough energy, and this is what makes silicon partly conductive. But what makes silicon ultra useful is doping. When doping, elements are inserted into the silicon structure that are foreign. If phosphorus with 5 outer electrons is inserted, the structure has suddenly an excess electron. This is called an n-type semiconductor. If, on the other hand, aluminum with 3 valence electrons is inserted, the structure lacks an electron, which creates a place where there should be an electron in the structure but where there isn't, a so-called electron hole. This process also increases the conductivity as the electrons move inside the structure to fill up the hole, which again creates a new hole at another place. However, we like to think that the holes are moving, and as holes lack electrons, we think about them as moving positive charges. We call this structure a p-type semiconductor. Even though their names are negative and positive type semiconductors, they are not charged negatively or positively. They have the same number of protons and electrons inside them. The terms N and P-type semiconductors only refer to the sign of charge that can move. These properties become only useful if we add these two doped semiconductors together. If we put an N-type semiconductor next to a P-type semiconductor, we get what is called a p-n junction. In the border between the two regions, electrons move from the N region to the P region to fill the electron holes. This creates what is called a depletion region, in which there are no freely moving electrons or holes. A slim region of the P side becomes negatively charged, while a slim region on the N side becomes positively charged. This creates an electric field, which prevents more electrons from moving from the N to the P side. The depletion region acts like a barrier. When we now connect a voltage source to the PN junction with the positive pole connected to the P side and the negative pole connected to the N side, we push the electrons to move from the N side to the P side. This is what we call forward bias. However, for the movement to occur, the pushing force, the voltage, must be high enough to overcome the barrier. If the voltage is higher than 0.7 volts, the barrier is overcome and the PN junction becomes conductive. If we reverse the polarity of the battery, we connect the positive pole to the N side and the negative pole to the P side. Something entirely different happens then. The electrons on the N side are attracted to the plus pole, while the holes on the P side are attracted to the minus pole. Therefore, the depletion region or barrier expands and no current can flow. What we just created is a diode. A diode is an electrical component that uses a PN junction to only allow current to flow in one direction. The symbol of a diode consists of a triangle with a vertical line and a horizontal line. The side of the triangle with the vertical line represents the cathode, while the opposite side represents the anode. Forward bias occurs when the diode's anode is connected to the positive pole and the cathode to the negative pole. This configuration allows current to flow through the diode in the direction of the arrowhead of the symbol. We can use a standard diode on our flight computers to protect them from reverse voltage or to rectify alternating current to direct current by a full wave rectifier. However, there are also other forms of diodes. The ones most notable for flight computer design are the Schottky diode, the light emitting diode, and the Zener diode. The Schottky diode uses a metal semiconductor junction instead of a PN junction. By utilizing this junction, Schottky diodes can achieve faster switching speeds and exhibit lower forward voltage drops compared to their PN junction counterparts. Due to their ability to operate in fast switching speeds and their low dropout voltage, we often use them on switching voltage regulation circuits. Light emitting diodes, or LEDs, emit light when current flows through them. They find widespread use in flight computers for status indication, such as power indicators, system alerts, and communication status LEDs. LEDs are available in various colors, making them ideal for visual feedback in electronic system. However, they require the use of a current limiting resistor, as they otherwise could become permanently damaged. Unlike standard diodes, which conduct current in one direction only, Zener diodes can also conduct in the reverse direction when the voltage exceeds a specific threshold called the Zener voltage. Zener diodes can be used to protect our flight computer input channels from overvoltage. When atoms bond covalently, they share their outer electrons to reach a full valence layer. There are conductors, isolators, and something in between that is called a semiconductor. The widest used semiconductor material is silicon, which is a crystal-like structure. The silicon structure can be doped by adding phosphor with an extra electron to create an N-type semiconductor, or by adding aluminum with a lack of an electron to create a P-type semiconductor. In the N-type semiconductor, electrons can move freely, while in the P-type semiconductor, electron holes move freely. When placing an N-type semiconductor next to a P-type semiconductor, we get something that is called a PN junction. Some of the electrons move to the P side to fill up the holes, which creates an electric field that prevents further movement. If we apply voltage in forward bias, this barrier can be overcome and the material becomes conductive. If we apply voltage in reverse bias, the holes move to the negative side while the electrons move to the plus pole of the battery, which makes the barrier even bigger and allows no current to flow. Through that, we have created a component which allows current to flow in only one direction, which we call a diode. A diode can be used to protect our circuits against reverse voltage or to rectify alternating current to direct current. There are special diodes such as LEDs, which light up in forward bias, and Zener diodes, which allow us to protect our devices from overvoltage. The full course is available on Udemy.